Hi, everyone. So today I'm going to be going over question 4 of the worksheet. So question 4.1 asks us to draw the 2-3 tree after inserting 18, 12, and 13 in that order. So let's see what happens when we insert 18. So what happens is we're going to compare 18. So we're going to start at the root, and we're going to compare 18 with the value of the root, which is 8. We see that 18 is greater than 8, so we move to the right child. When we get to the right child, we see that 18 is greater than 14, so we move on to 14's right child. When we get to this node here that contains 15 and 16, we should see that 15 and 16 is a leaf node, so it has no left and right child. So we have to insert 18 into this node. However, when we insert 18 into this node, we've created a node that has 3 elements in it. And when this happens, recall that we need to push the middle element up and then separate the left and right elements. So we push 16 up and we split 15 and 18 into separate nodes. So this is what the tree should look like after we insert 18 into the original tree. Great. So now let's see what happens when we insert 12 into the tree. So we again start at the root. We compare 12 with the root. We see that 12 is greater than 8, so we move on to the right child. We see that here, 12 is less than both 14 and 16, so we move on to the left child. And here, because we reached the leaf node, we have to insert 12. We insert 12 to the right of 10 because 12 is greater than 10. So this is what the tree looks like after we insert 12. And so now what happens when we insert 13? Well, again, we're going to start at the root. We see that 13 is greater than 8, so we go to the right child. Here in this node, we see that 13 is less than both 14 and 16, so we go to its left child. And here, again, because this node containing 10 and 12 is a leaf node, we have to add 13. We add 13 to the right of both 10 and 12 because 13 is greater than both of them. And as a result, you get this node here. But notice, again, we've created a node that contains 3 elements in them. So what we have to do is we have to push 12 up and then split 10 and 13 into separate nodes. So this is what we get. But again, we notice that we've created a node with 3 elements in them. So we have to push the middle element, in this case 14, up, and then split 12 and 16 into separate nodes. So we push 14 up so that it has the root node now can say 8 and 14. And then we split 12 into its own node and 16 into its own node. And there we have it. This is the resulting tree after we insert 18, 12, and 13. Let's look at 4.2a. 4.2a says, for a node in a 2-3 tree with n values, what are the possible number of children that each node can have? What if the node is not a leaf? So let's split this into 2 cases. Let's consider when a node can either be a leaf or a non-leaf. And let's consider the case when we're dealing with nodes that are non-leaf nodes. So recall that, so let's consider the case when n equals 1. So when there's only 1 element in a node. So recall that one of the characteristics of a 2-3 tree is that when there is only 1 element in a node, it can only have either 0 children or 2 children. So that's what we have here. When n equals 1, you can either have 0 or 2 children. But then recall that the only way a node can have 0 children is if it's a leaf node. So when we're considering non-leaf nodes, when n equals 1, there can only be 2 children. Okay, so let's consider the case when n equals 2. Recall that one of the characteristics of a 2-3 tree, when there are 2 elements in a node, there can either be 0 children or 3 children. So when we're dealing with both leaf and non-leaf nodes, there can be 0 or 3 children. However, again, a leaf node has 0 children. That's like the definition of a leaf node, right? So when we're dealing with purely non-leaf nodes, we can only have 3 children. So that's what we have for 4.2a. Great. Let's move on to 4.2b. So 4.2b says that instead of splitting an overstuffed node by moving the middle value upwards in the tree, suppose we move the rightmost third value of the node. Can we still guarantee the idea of a balanced binary search tree with a 2-3 tree using the splitting method? Okay, so let's consider this tree here that contains elements 1 and 2. And let's say I call insert 3. When I insert 3, I'm going to put 3 to the right of 1 and 2 because 3 is greater than both of them. And then our splitting method says that we're going to push 3 up. When I push 3 up, 3 has a left child that contains 1 and 2, but has no right child. And this is going to cause the tree to be unbalanced. So this is kind of like the counterexample that says that, hey, we can't use the splitting method to create a balanced search tree. But conceptually, how does this work? Well, when we're splitting the middle value up, we're kind of naturally creating a balanced left and right branch because we're using the middle value. But when we use the right value, we're going to cause the left branch to be heavier than the right child, right? So there's going to be more children on the left branch than the right branch if we're using the rightmost element. And this is kind of like the conceptual understanding of why there is this imbalance. Okay, so that's 4.2b. Let's move on to 4.2c. 4.2c asks, what is the maximum height of a 2-3 tree with n values? So let's consider what happens when our 2-3 tree looks exactly like a BST. And let's imagine that all nodes in the 2-3 tree has only one element, so has no overstuffed nodes. So why are we considering the case where there are no overstuffed nodes? Well, you can imagine that if we have a 2-3 tree where all nodes have 2 values in them, then the height of that tree is going to be smaller than a 2-3 tree that has the same amount of nodes, but with only one element in them. And what we should notice is that we know that balanced BSTs have a height of theta log n. So if a 2-3 tree has no overstuffed nodes and looks like a balanced BST, the overall height of our 2-3 tree in that case would be theta log n. So the maximum height of a 2-3 tree with n values is theta log n, which is great, by the way. We get the nice theta log n runtime. Okay, let's look at 4.2d. So 4.2d says, is it possible for leaf nodes of a 2-3 tree to have differing distances to the root? If not, explain why. Otherwise, provide an example 2-3 tree that satisfies the condition. So the answer to this is no, this is not possible. And let's consider 2 cases when we insert into a 2-3 tree. So the 2 cases is that the element gets stuffed into a leaf node, and we can imagine like the leaf node previously only had one element in it, and that's not going to increase the distance from the leaf to the root. The second case is that we insert into a node and causes the node to have 3 elements in it. In that case, we're going to move the middle element up and split the left and right child. This also isn't going to increase the distance from the leaf to the node. And the key idea behind increasing the height of a 2-3 tree is that we only going to increase the height when we split the node at the root. And you can imagine that's going to happen after a chain of middle elements being pushed up. And so that's the only time we can increase the height of the tree. And as a result, the branches themselves can't grow individually. And furthermore, when the root node gets split, this is going to increase the distance from the root to every leaf node by 1. So it's not going to increase the distance from the root to one leaf. It's going to increase the distance from the root to every leaf. So yeah, the distance between the root to the leaf is going to be the same even after we split the root node.